Hello, George Notchik here. Today is Wednesday, July 31st, 2019. And yesterday somebody had asked me a question as how would the ancients have known that between the earth and the sun you can fit around 107 suns, or there's 107 sun diameters between the earth and the sun, and just as many moon diameters as there are between the earth and the moon. That is, if you take the diameter of the moon divided into the distance between the earth and the moon, the number's around 107. And likewise, if you take the distance between the earth and the sun and divide by the diameter of the sun, you get around 107. The numbers are close together. And so question is how would the ancients without any modern equipment know this? And on the surface it sounds kind of curious. Well, how would they know that without the current technology that we have in knowing what the diameter and the distances are? Well, turns out the answer is really quite simple. I was thinking about it while I was walking the dog yesterday, and the answer is really quite simple. And it doesn't take a whole lot of sophisticated instrumentation or mathematics to understand how ancient people could know this. So, suppose here we have the surface of the earth, here we have the moon, here we have the sun. Now we know from our perspective here on the earth that the angular sizes of both the sun and the moon appear to be about a half a degree. That is, if you're standing here and you're peering at the moon and the sun, they both fill up this cone almost exactly. That the moon, angular diameter of the moon from someone standing on the earth looks like it totally covers the sun. And we notice that during total eclipses, that the disk of the moon will totally cover the disk of the sun. Now, the Greeks were real good geometers. They understood how to do constructions with straight edges and compasses, and Euclid developed a whole set of mathematics and produced a book called The Elements that had to deal with geometry, dealing from first principles. And so the Greeks really did know about triangles and relationships to angles and side lengths and angles and that on triangles, and also other figures, plane figures. But we only have to look at triangles. Notice here, as we're, say, on the earth peering out at the sun and the moon, we see this triangle. If we draw lines from the earth to the edge of the moon and the edge of the sun, we define these two triangles and we have these diameters. So what we have here is basically what we call an isosceles triangle, where two of the side lengths are the same length. That is, we're sweeping out this angle with the same distance to either the moon or to the sun. And we sweep out some angle theta. Well, the Greeks knew the properties of triangles and similar triangles. If we look, we have a triangle here, we have a triangle here, we have a triangle here. We can have any number of what we call similar triangles. That is, they have the same interior angles, though the side lengths might be different. So, if that is the case, if we're defining similar triangles, then the ratio of the sides are all the same. That is, we could write that the distance R1 along this side length to this side, so we have R1 to D1, is going to be the same as this side length is to this side length, or as R2 is to D2, as R3, this length, to this side length, or for any number of similar triangles. So we can draw all kinds of similar triangles, and as long as a sub 10 have this one of the apex angles being the same, and the other two angles being the same. Remember, this is an isosceles triangle, so the sides opposite the two sides that have the same length have the same angle. So this angle is the same as that angle. And that being the case, then these this side ratios for similar triangles hold. And you can use trigonometry to also prove this, but you don't need trigonometry to solve this problem. So what we have here is two similar triangles. This is our angle theta. We really don't need to know what theta is. We don't have to measure it in terms of degrees or radians. All we need to know is that this same angle subtends the diameters of both the sun and the moon. So in this case, we can write that the distance to the moon divided by the diameter of the moon is going to be the same as the distance to the sun divided by the diameter of the sun. So if we know one of these ratios, we know the other one. So this answers the first question, is how would anyone know that the ratio of the number of diameters of the sun that can fit between the sun and the earth would be the same as the number of the diameters of the moon that can fit between the moon and the earth. That's given by this ratio. Now, what is that number? How do we determine what that number is? How did the ancients know that it might be 107? Well, what you can do is build a very simple apparatus, like I did here. I took 2 meter sticks. I have 2 meter sticks here, and you can see I put 2 indicators, one on the end of each one, on the end of each meter stick, and I have them attached at a fulcrum here where I can spread these apart to measure this angle. But I don't need to know what that angle is. All I have to do is take and sight this and get it to fit between the two edges of the sun or the moon. And then by knowing the length from my eye on sighting to the 2 pegs and the distance between the 2 pegs, I can get this number, because again, this ratio holds for any similar triangle. Well, we have 2 similar triangles, one going from my eye to the moon and the other to the sun, and I also have this one, which is a much shorter one. We have a much shorter length and a much shorter diameter, so to speak, going between the 2 pegs. So what we have here is, say this is the moon, this is the sun, or say this is the moon, this is the sun, and here's my measuring apparatus using the 2 sticks. And this is much shorter. So if this is, say, the moon, and this is the sun, and this is my measuring apparatus. So the ratios are all going to be the same. So if I have my measuring apparatus, I'm sighting, say with my 2 pegs, I've got one here and one here, and that's going to fit in this triangle, and I know that the distance here is 1 meter. I'm using meter sticks. You could use a lot longer sticks to get a more precise measurement, but it's 1 meter, and once I sight it so that the pegs are on either side of the sun or the moon, I can measure that distance x. So then this becomes the ratio of x to 1 meter, and I measure x, say, in terms of meters, or I could put this in terms of centimeters. Say it's 100 centimeters. And I went outside and I did just that. I measured several times on the sun. I had some protective glasses on so I could sight the pegs on either side of the sun. And I'm sorry, the ratio is the other way. The length is 100 centimeters, and we're dividing by x. Well, x in terms of centimeters, I measured it several different times, and it was came out to about 9 millimeters. One time I got 9 millimeters, 8 millimeters, 10 millimeters, but the average came out to about 9 millimeters or 0.9 centimeters. Well, if I take 100 centimeters, divide by 0.9 centimeters, this comes out to about 110. That number. So this number came out to about 110 for me on average. Now, let's look at the actual data for the sun and the moon. Okay, the diameter of the moon is 3,474.2 kilometers. Diameter of the sun is 1,391,000 kilometers. And what I've got here are 3 different sets of data. Remember that the moon and the sun don't have perfect circular diameters. Or the orbit of the Earth about the sun and the moon about the Earth are not perfect circles. They're ellipses, and they have a furthest distance and a closest distance to the objects that they orbit. So in the case of the moon, we have an apogee, which is the furthest distance from the Earth, of 400,000 kilometers. The average mean distance of the moon to the Earth is 384,400 kilometers, and at the perigee, which is the closest approach the moon has to the Earth, it's 362,600 kilometers. Now if I ratio them, if I take the distance divided by the diameter of the moon, these are the numbers you get. When the moon is at apogee, that ratio is 116.7, the mean is 110.6, and at perigee, at the closest approach, it's 104.4. Now the same thing for the sun. We have aphelion, perihelion. At the aphelion, the sun is furthest, or the Earth is furthest from the sun at 1.5 to 1 million kilometers. The mean distance the Earth is from the sun is 150 million kilometers, and at perigee, the closest approach, the Earth is 1.471 million kilometers. And if I ratio the distances the Earth is from the sun to the diameter of the sun, we get 109.3 at aphelion, mean is 107.8, and at perihelion, at the closest approach, that the Earth is to the sun, we get 105.8. So we see the similarity of these numbers. There are going to be points in the orbit that the Earth has about the sun and the moon has about the Earth where the numbers will exactly match. But if we were to average these things out, the average for the moon is at 110.6, and the average for the sun is 107.8. So they're really quite close together. And again, you can use an apparatus such as this, where you can sight the sun or the moon, and then once you do that, you measure the distance with a measuring stick or a ruler between the 2 pegs, and knowing the distance along the length to your eye, you set it up so that your eye is at the end here like this, and then you sight so that the pegs appear on either side of the sun or the moon, and then once you get it, you clamp it down and then measure the length between the pegs, and knowing that this length is 1 meter, we can compute the ratio and get how many sun diameters and moon diameters fit between those respective bodies and the Earth. So that's how the ancients could do it. No real powerful mathematics needed, just ratios. And to construct a cheap little apparatus, you can do it with a high degree of precision. This is rather crude. You could use a lot longer sticks and have it with precision machinery and really get it close in so you can get better accuracy on these numbers, but it illustrates the principle, and that's how the ancients could have known that the moon and the sun, the number of diameters of those bodies between the earth and those respective bodies, have a number very similar to one another. It's around 110, 107 to 110, just depending upon where in the orbit the earth is about the sun and the moon is about the earth. And the another way to look at it is with perspective. The perspective equation is that the distance on arc swept out by some radius is given by r times theta, where r is your arm, and this is going to sweep out through some angle theta, and it sweeps out that length. So we can see that if we solve for theta, theta is d over r, or 1 over theta is r over d. And in a given triangle, where we have similar triangles, they are all swept out through the same angle theta. So we could have r1 to d1, r2 to d2, and they're all equal to this same angle. That's the because we have similar triangles. So these ratios are going to be the same because they just represent 1 over the angle that's being swept out. That's what these ratios represent as a consequence of similar triangles. So there you have it. That's why the ancients could have known this. Okay, I have my measurement apparatus set up here to measure the desktop globe I have set up in the distance by an outside window. The globe is 12 inches in diameter, and I measured the distance from the apparatus to the globe with a carpenter's tape rule. It's 295 inches. And you can see that I have the pegs set up on either side of the globe to measure its diameter. And now I'll measure the distance between the two pegs. We know the distance from the pegs to the eye at the fulcrum of the two sticks is 100 centimeters, 1 meter. And now we'll go ahead and compare to see how the numbers compare with the actual distances measured and using this crude little apparatus that I made. Well, we just finished measuring the desktop globe. Here I had by the outside window a desktop globe. It has a diameter of 12 inches, and over in the distance on the other side of my room I had my 2 meter stick measuring apparatus aimed at the globe, and had the two pegs sighted in on the opposite edges to measure the diameter of the globe, the angular measure. And after I was done, I took a carpenter's rule and I measured the distance from the center of the globe to the eye sighting point as 295 inches. And then the separation distance between the pegs, that was a little over 39.5 millimeters. We'll just call it 39.5. And then, of course, the meter stick length is 1 meter or 1,000 millimeters. So again, we have similar triangles. We have 12 inches on the diameter with a distance of 295 inches. And then with the measurement apparatus, we have 39.5 millimeters with a distance of 1,000 millimeters. Now the units don't matter. we can mix the units because we're ratioing them. The units drop out. So let's compare. For the globe, the distance is 295, and dividing by 12, we get 295 divided by 12. That's 24.6. And if we take the measurement apparatus, we have 1,000 millimeters divided by 39.5. So 1,000 divided by 39.5, that comes out to 25.3. So it's pretty close, given, you know, how crude the setup was. The difference, the error that I have here between the two, is 2.9%. So not too bad, given the crudeness of my measurement apparatus. So it shows you the principle that with the ratioing the sides of a cylinder or triangle, that the numbers will come out, the ratios will come out to be the same. And so that's how the ancients could have known how many sun diameters could fit between the Earth and the Sun, and how many moon diameters fit between the Moon and the Earth.